Please welcome to the stage Chris Leptokaridis.
Hello. Welcome and good evening. My name is Chris Leptokaridis. I'm the technical director of Saudi Ready-Mix. Saudi Ready-Mix is the largest producer of ready-mix concrete in Saudi Arabia. And therefore, it is our responsibility to think of the impact a product has in the environment. And this is what we're going to be discussing today: the environmental impact of concrete, climate change, what the industry can do to mitigate this, and concrete as a future material. A lot of you would be surprised to hear that concrete is the second most used substance in the world after water. We consume enormous amounts of it. Every piece of infrastructure you see around you in every modern city is built out of concrete. And there's a reason for this. Concrete is a great material. It's strong, it's durable, it's waterproof, it's fireproof, and most importantly, it can actually be made by local materials in every corner of the world. But there is one thing that concrete is not. Concrete is not very environmentally friendly. In order to make concrete, you need to take stones of different sizes and bind them together using a glue called cement. Cement, in turn, in order to produce it, you need to burn enormous amounts of limestone and coal, and clay in kilns at very high temperatures. There's a chemical reaction happening there which emits a lot of CO2. Actually, that chemical reaction it's responsible for 3% of the world's global emissions. The total cycle of concrete emissions is about 10%, 8 to 10%. So that's a lot of CO2. So the next question, obviously, is there something we can do about it? Can we use a different material? Can we maybe not use cement? Power stations, dams, bridges, high-rise buildings, stadiums. Everything we associate with the modern world is actually built out of concrete. There is no other material that can give us the same benefits or basically give us anything close to it. So we have to find a way to make concrete more environmentally friendly. First of all, let's see what the damage is. A single ton of cement, when you produce it, emits 800 kilograms of CO2. If you translate that into concrete, a cubic meter of concrete emits 350 kilograms of CO2. Keep that number in your head. So we need to take that number down. First of all, we can replace part of the cement. We can use supplementary materials that are waste byproducts of a different industry, such as silica fume, slag, fly ash. These materials are carbon neutral, they consider to have 0 emissions, and can help us take that number from 350 to 200. In Saudi Ready-Mix, in the last 7 years, we have used a lot of these materials. We have actually avoided the emission of more than 1 million tons of CO2. You use that materials in percentages between 20 to 70%. Let's take 50% as an average. And you go down to 200 kilos of CO2. The next step is to look at the production of cement itself. Look at the cement factory. There are multiple technologies that can help us reduce the environmental impact of cement production. Alternative fuels, biomass in the raw materials, preheaters, grinding, a lot of different things. No cement plant is using all these technologies at the same time. But if they do, and when they do, they're going to reduce the emissions down to 150. But we still have 150, and we still have a lot of CO2 going up in the air through our chimneys. So what do? We use a new technology called carbon capture. And we take that 150 kilograms of CO2, and we try to put them down in a hole in the ground, in a geological formation. Usually, these geological formations are exhausted gas fields. You can store them there safely and indefinitely. If you don't have an appropriate formation nearby, there are other technologies. You can force them to react with a mixture of recycled concrete and minerals and effectively lock them into stone. Or you can even feed them in pools of microorganisms like algae. The waste of these microorganisms will actually produce a form of biodiesel, which you can then feed back into your production, creating a virtuous cycle. So in this way, you go down to 60. What is the remaining 60? The remaining 60 is mostly due to the transportation, heavy vehicles burning diesel, and the electricity we're using in our own production facilities, in cement factories, in concrete plants. The answer to this is obvious. Heavy vehicles have to be electric, something that will happen in the next few years, and the electricity itself has to be produced by renewable sources of energy, so wind, solar, nuclear. This is obviously something that a state has to step in and do it. So there are things that the industry can do, there are things that countries have to do, but there are also things that engineers, designers, and architects can do from their side. So first of all, what we can do as engineers and architects is design for durability and design for sustainability. We can design sophisticated mixed designs that use less cement and last longer. As architects and as designers, you can ensure sensible floor loading, or you can avoid unnecessary finishes or materials. But let's concentrate on two things that are closer to our industry. So first of all, design for durability. It is obvious. If you design a building which lasts longer and requires less repairs, it's going to be greener than a building that has to be demolished in 30 or 40 years, even if that building, on paper, initially, was actually more environmentally friendly. So you have to design with the idea of changing uses in a building. The Roman Pantheon is an obvious example of that. But eventually, there's going to be a building will reach the end of its service life, and will have to be demolished. So then we have to design and understand what will these raw materials, what will happen to these raw materials after the demolition. Can they be recycled? Can they be reused in another industry? So it's the whole concept of cradle-to-cradle design. Design for the next building. So I gave you a brief outline what the industry is trying to do and the challenges we're facing. And we have a specific target. Every cement and concrete association around the world has a date, and the date is 2050. By 2050, we have to be carbon neutral. We have to produce cement and concrete with zero carbon emissions. But there are many other technologies at the same time which we're researching in parallel. So yes, it's going to be carbon neutral, but can also be fiber reinforced. And when I say fiber reinforced, can we actually produce a concrete with enough tensile strength that you don't need steel? Because most of the problems of concrete in terms of durability comes from the corrosion of steel. And if we do that, can we then use that material through a 3D printer and automatically print a house with no labor, very high quality control, effectively building a house in the same way as we built a car? And beyond that, can we actually monitor its performance? Yes, we can put smart sensors, as we even now. But can we turn the entire material into a smart sensor? If we use carbon nanotubes, a technology that has been developed in the last 10 years, we can actually give concrete a specific and measurable electric conductivity that changes depending on the stresses it's under, either mechanical or thermal. And then we can read that signal and interpret it and act on it. So basically, monitoring passively forever. And how about heating and warming a building? Phase-changing materials are not new. The materials that absorb or emit energy depending when they change phase. Water is a phase-changing material. But if we use this phase-changing material, and this is something that happens only in the last 5 years, it's very, very recent research, we can actually use a phase-changing material into concrete that can heat and cool a building, or at least helps us to do it, automatically, with no input from us at all. And how about throughout its life? Eventually, concrete will crack. Any building will need repairs. How about if we have actually put compounds in there that can react with the moisture from the air, create new compounds, and heal the cracks, bridge the gaps, organically, like a broken bone heals. And at the end, you have a material which is even stronger than the material you installed. This, again, is a technology which has been going on for the last 10 years. All these are not fantastic technologies. They're all under research, and they're all, hopefully, going to be the reality in the next 10 to 20 years. So I hope I gave you an outline of where the technology is in concrete, the challenges we're facing, and what we're doing about it. I would love to talk more. We don't have a lot of time. There's going to be many more other interesting presentations. Thank you all for your time and attention. Thank you.